In addition to these statistical properties, another important concept is probability. So, in order to explain the probability, we generally define events. So, event B is defined like when your velocity is less than some velocity, and event C is defined like your velocity is between two values. So once we have events defined like this, what we do is to define probability of events. So the probability of B, for example, is equal to P of B. So it is the probability where your velocity is less than some specific velocity VB. In order to handle the probabilities, we have to relate them to some analytical functions. So the first function in statistics is what we call as cumulative distribution function, or CDF. CDF is defined as f of v, and it is the probability of u being less than v. So uh, in here, uh, f of vb will be defined as the probability of u uh, being smaller than vb, for example. This is really an analytical function, so you can plot it like you see. Uh, the question is, how does it look like? And is it a polynomial? Is it harmonic function? Is it exponential function? What is it? So uh, just consider that you don't know what this is the shape of the CDF. You just analyze it at minus infinity and plus infinity. So uh, minus infinity refers to the fact that probability of u, so being less than minus infinity, what could be its numerical value? So probability of velocity, for example, being less than minus infinity. Is it possible? Is it probable? No. So it is zero. It can never be less than minus infinity. So f of minus infinity is zero. So what about plus infinity? Plus infinity meaning that probability of u being less than infinity. So that's true. It's always true because your velocity is a finite value. It won't go to infinity, so it will be equal to 1. So the numerical value of probability changes between 0 and 1. So the function actually will change between 0 and 1, as you see. This is a CDF function. CDF is a statistical sense, and it's very important. But in terms of mostly engineering applications, more than using CDF, we use another function, which is in fact the mathematical derivative of CDF, and we call it as probability density function, or PDF, not the PDF that you are using in your computer, but probability density function, and it is defined by the actual derivative of CDF. So it is exactly the derivative of CDF. And if you plot this f versus your uh, velocity diagram, it mostly like it looks like this that you're seeing, and the value of f at its limits will be um, 0 and 0. So you will have no slope in a capital F diagram. If you go back, you see that there is no slope at capital F diagram. So it should be both at limits, the CDF is flat, hence the values are both 0. So we are talking about a function which is 0 at its both ends, and there could be some variation in between. If you calculate the area underneath the PDF, so if you just calculate this area, it would be equal to 1. Okay, so because it is in here, it's 1, and that's actually the whole probability. So it says that the whole probability is 100%. That's why this area is equal to 1. Uh, so you can just compare the PDF and CDF in this graph as well. So PDF is like this red one, and the CDF is like the green one. The derivative, and these are not very important. I just want to mention the relation between PDF and CDF. We know some of the well-known or well-established probability density functions. For example, the previous figure is a bell-shaped curve. This curve, a bell-shaped curve, and we know it as a Gaussian distribution. This distribution has some analytic formula. This is its formula, analytic formula, and it is a continuous function. So therefore, you can take its integral as well. So if you take the integral, you will get with this function, which is analytically known. Uh, how do I calculate the probability of velocity being less than, for example, some other velocity when you see it in here, or and greater than some other velocity. If this PDF is given, you can calculate the area underneath between two velocities. So, for example, this velocity and this velocity, this area actually tells you the probability velocity between uh, of velocity between these two values. This is not the only PDF, as I said, that exists. Uh, this is the only one of them that can describe the probability of an event. There could be other functions, for example, Weibull distribution, Rayleigh distribution. We can have these two. Depending on your physical variation, a Gaussian distribution could represent it better than Weibull. In some case, it is opposite. For example, in wind energy, we predict wind based on the data, and those wind data are represented most of the time in industry by Weibull distribution. But another example is the student grades, which most of the time are presented by Gaussian distribution or Gaussian function. So this figure in here at the left hand side is the Gaussian distribution of some data represents, and it represents that, for example, 68.26% of the data happens in between -1 and 1 standard deviation. And if we widen this range to -2 and 2 standard deviation, it says that 95.44% um, of data will be encompassed inside, and so on. One of the fields in terms of engineering applications, we use them in characterization of droplet size, for example, in spray injectors. For a gas turbine engine, for example, in the combustion chamber, you have injectors to inject the fuel, or in liquid rocket engines, you inject the fuel. The thing, the thing is, in order to be able to predict how much the temperature distribution is going to be, one of the important properties that you need to know is how big the droplet size will be once you inject them. I- Would it be 100 microns or 1000 microns? The answer to this question is that we don't know the exact answer, but what we can provide using some experimental results is probability distribution of these sprayed particle sizes. The droplet sizes can be measured using laser-based techniques, and then using that measured droplet size, we determine these functions that represent the droplet size distribution. So these are the distribution, and give those functions to people who are going to simulate the combustion characteristics, for example, in a gas turbine or in rocket engines. So you see two different distributions. One is the PDF and one is the CDF distributions of these droplet sizes. I also included the um, source that I just took the graphs from. Okay, I hope that you're not tired. These are very important things. In addition to what we described, there are other parameters that are relevant in statistical calculations to make sense of the signals. And as I told you, these are called moments. And what I'm going to describe is centered moments. The first one is variance. So variance is denoted by sigma u squared, and it is equal to the average of u1 minus u1 bar squared. Uh, Actually, this power in here, the power of 2, is to make it irrelevant from being positive or negative. So this is every time it is a positive number. And then based on the variance, we define the standard deviation or RMS value, and it is nothing but the square root of variance. So RMS is the root mean square, and we call it as the standard deviation. This tells that this standard deviation, as you saw it in here, I said between minus and 1 or minus 2 and 2, these are standard deviations. This actually tells me that most of the data I have is changing within plus or minus of standard deviation, plus or minus of RMS data band. This is a band of data. So this is one standard deviation. For example, this is two standard deviation. This is three standard deviation. It's a band of change. Variance and standard deviation are very basic uh, statistical quantities. And just as an example, let's consider this velocity variation again. It's just an example. So you see when I calculate for the deviation is sometimes positive. You can see uh, here, and sometimes it could be negative. So I just gave 2 times as time in here 40, and then this time 41. So the deviation means the velocity minus the mean. Mean is this orange line, the average of the data. So exactly at time equal to 40 seconds, the deviation is negative. You see it in here. And 1 second after that, the deviation became positive. What you do is you calculate this deviation for every point in time, and then you take its square to make it irrelevant from being positive or negative, uh, and then you add them up and then take the average. Okay? If you This is the definition of RMS, root mean square. You square them, you take mean, and then if you get the root, square root of that, you will get the standard deviation. If you don't take the square root, you will obtain what you call as the variance. So, for example, if this average, this orange line is something like this, and I somehow calculated the instantaneous velocities I have, and uh, let's say if I somehow calculated this variance or and standard deviation, my if I find that my standard deviation is, for example, 2.8, and this has a unit of velocity again, what this value tells me? It tells me this. It tells me most of the instantaneous data in here, or the velocities that I measured, will change between the average value, between average value, which is 4827 plus minus 2.8. So a standard deviation tells me this. Most of the data is changing between, for example, 7 and 3 and 7 meters per second. So if I take this and this, and if I take this band, let's say 3 and 7, you will see that directly that the most of the data is changing between these two. I need to answer a call. Just give me a minute. Okay, so if I just draw this band, as I said, you will see that the most of the data, most of the points will be grabbed within this band of the data. So this is the standard deviation, and uh, let's say it is in this range, and you could have data lower than this, let's say, band, and higher than this limit, but uh, that is not very frequent, as you see. So some data is here, some data is at the bottom, but that is not very frequent. This is the information that we are getting from the standard deviation calculation. And if you sort the velocity data, this velocity data, if you sort it and count the numbers of data in the range of 4.8 plus minus 2.8, um, it will include what I did. It will include 66 velocity points. It means that okay, I have 100 data sets, so 66 of them are within this band. So 66% of my data is within my standard deviation. The variance and the standard deviations are, as I said, not the only moments in statistics. We have some other higher order moments as well. And we mentioned the general statistical definition for moment is like this. And we mentioned skewness and flatness in some slides before. So the general definition is like this. The moment Q, I mean, the order of the moment is Q. So qth order moment is equal to u minus u bar to the power of q bar, so average. So for example, m2, denoting that the second order moment or my variance is u minus u bar to the power of 2, and then get average. So I can define the skewness of a signal by, uh, let's say, third order moment over second order moment to the power of 3 over 2. This skewness, physically, it denotes the asymmetry of the signal. So as you see, I have a signal like this in here, and the skewness tells how symmetric is your signal around your mean value, around your this orange line. So what do we mean by the asymmetry of a signal? If your signal spends most of the time fluctuating above the mean, but once in a while, a very peak, you have a very big peak in here once in a while, again and again and again. So, but most of the time it is traveling above the mean. So this signal is not symmetric. Most of the time it is in one side of the mean, and a few times it is on the other side. But uh, the values are big, so they can compensate the average. A symmetrical distribution would have more or less fluctuations around the mean. In order to quantify this kind of variations, we use the skewness. So skewness of, for example, this signal, I just plotted the skewness of the signal, and sorry, I just plotted the histogram. I will tell you what is the histogram. I just plotted the histogram of this signal, and I obtained the skewness of the signal equal to, let's say, minus 1.27. So it is minus, it is a negative skewness. And uh, when you are able to plot the histogram and PDF of such a data, you could have this variation. And the histogram shows the frequency of velocities. Uh, so frequency of velocity, meaning that the how many times you have some velocity, okay, in this signal. So for example, as you can see, this velocity is changing between 0 and 10 meters per second. So if I divide it between 0 and 10 with 10 different bars, it says that, okay, how many times you have zero velocity, how many times you have 1 meter per second velocity, how many times you have velocity equal to 2 meters per second. So this is, if you just sum up these values, you will end up with 100, because this represents that all of the data. So you will just sum up the values and you will see. So this is the histogram. So it says that there is no velocities in the range of 0 and 1, for example. This is a range. And there is 16 number of velocities between 1 and 2 meters per second. It goes like this. So this is the histogram. So you just saw that the PDF shape of a signal with with negative skewness is like this. So I'm giving you the comparison in here. So as you see, uh, this is a negative skewness of a signal, and this is a positive skewness of the signal. In addition to the fact that a standard deviation tells us the general band of deviation around the mean or around the average, the skewness tells me the general symmetry of the variation around the mean. So looking at these, uh, you can somehow get familiarized with the skewness. So if you look, this is a symmetrical data, this is a symmetrical distribution, and the negative and the positive distribution is given like this. Okay, I think I should tell you this, and yes, let me finish this part. In addition to all of these, there is one final parameter which also gives another information to us, and it is called flatness. Sometimes in the literature, you will see it as kurtosis. So it's called kurtosis or flatness. This is also a higher order statistical moment. So flatness of U, flatness of a signal, is defined by the fourth order moment divided by second order moment squared. All of these moments are characterizing some features of the original signal. And we talked about the standard deviation, we talked about the skewness and how it actually indicates the symmetry of the signal. This one, flatness, as its name suggests, indicates how flat your signal is. What I mean by flat, I just gave an example in here to you. We could have the same uh, mean value. So in here, the mean value is about, I think, 3 or 4 meters per second. This is the mean value by two different signal patterns. So I have a signal, orange signal, and I have a blue signal. The black one is the average. So the orange signal has the orange signal has very little variation around the mean, and then it has very high peaks. The orange signal, the blue signal obviously does not look like the orange one, although they do have the same average, they do have the same mean. The values of flatness is when you uh, have all the data, and when you can calculate, you will get the flatness of blue equal to 1.7, flatness of orange equal to 3.42. So what flatness values tells us is that the blue signal um, has very high variance but not many high peaks. On the other hand, the original signal has very low variance, uh, but most of the time they are very clustered around the mean, except for few times that there are large peaks which could be negative or positive. So the orange signal could produce very low variance but high peaks exist, and we use these high order moments to, let's say, to get more information about our original signal. So I think this is enough for today. I already told you too much stories. So until now, we have covered the statistical notions that are needed in turbulence analysis. And we said that we started with averaging process, the difference between ensemble averaging, time averaging, what is a stationary, what is ergodic process, what is autocorrelation, uh, what physical importance it has. So it tries to tell us the size of the eddies that are passing through one point, how we calculate autocorrelation, and then probability, how we calculate the probability. So one thing we didn't talk about is how to generate PDF for a given signal. So I just told you PDF is the derivative of the CDF, and then we talked about the higher, let's say, it's higher order moments. So next week we will talk about the histogram and how do we generate histogram, and also how do we generate PDF of a signal. And I suppose that but by that time we will be ready to go to the Reynolds decomposition and averaging. That is the essence of the turbulence modeling.